Started. Okay. Good afternoon, all of you. I am Amit Kumar Shinde from Mechanical Department. Today we are going to discuss about iron carbide equilibrium diagram. So before going for the detailed description of the iron carbide equilibrium diagram, first we should aware about the cooling curve of the iron. Means what are the different phases will be there and what will be there crystal structure depending on the temperature, that will get explained in the cooling of the pure iron or cooling curve of the pure iron. And after that we will see the allotropic forms of the iron. First we will start with the different allotropic form of the iron. Now first, before going for the allotropy of the iron, we should understand that what is the meaning of allotropy. What is the meaning of allotropy? Allotropy means existence of the same material with the same chemical composition, but it will show the different structure depending on the temperature. For this, specifically for this iron, you will see that it will show two types of structures, that is BCC, body centered cubic structure, and FCC, that is face centered cubic structure, depending on the temperature. If you observe carefully from the room temperature, suppose on this side we are having room temperature, and from room temperature up to 910 degrees Celsius, it will remain in the BCC crystal structure only. When temperature reaches above 910 degrees Celsius, it will get transformed from BCC crystal structure to the FCC crystal structure, and it remains in the FCC crystal structure, that is the face centered cubic crystal structure, till the temperature reaches 1400 degrees Celsius, and above this temperature again it gets transformed to body centered cubic crystal structure, and it goes in the liquid state when it is heated above 1539 degrees Celsius. Now in this BCC structure, it will get divided into two forms, that is, one will be your alpha ion and another will be your beta ion. Alpha ion and beta ion. Then how this alpha ion and beta ion are classified depending on their properties, that is the ferromagnetic properties. The alpha ion from room temperature up to temperature 768 degrees Celsius temperature, it shows the ferromagnetism, that is, it is having magnetic properties, but when temperature reaches above this 768 degrees Celsius, it becomes paramagnetic in nature, and that will be known as the beta ion phase only. But during overall this temperature changes, it will remain in the BCC crystal structure only. So in this allotropy form, we have observed that, we have learned that the iron exists in the two different crystal structures depending on the temperature. If the temperature is up to 910 degrees Celsius, from room temperature up to 910 degrees Celsius, it remains in the body centered cubic structure, and if temperature is above 910 degrees Celsius and below the 1400 degrees Celsius, it remains in the face centered cubic structure, and this will be named as or termed as gamma ion. Then again above 1400 degrees Celsius, it gets transformed to body centered cubic structure, and it will be named as a delta ion. So these are different forms in which iron exists according to the temperature, and these are termed as the allotropic forms of the iron. Which are the allotropic forms of the iron? Alpha iron, gamma iron and delta iron. And what is the difference between this alpha iron and delta iron? That we will discuss in the cooling curve of the pure iron. We will discuss the next point, that is the cooling curve of the pure iron. All these basic concepts, that is the allotropic forms of the iron and cooling curves, what will exactly happen during the cooling of the pure iron from its liquid state to the up to the room temperature, that is going to help you to understand the iron and carbide equilibrium diagram clearly or easily. It will help you for that. Then next point we will discuss, that is cooling curve. This cooling curve of pure iron, already we know that. First we will see what is the meaning of cooling curve. First we will see what is the meaning of cooling curve. If suppose we have taken a metal or alloy, and from room temperature we have heated that alloy up to its melting point, it will get transformed to the liquid state. Then after getting to the liquid state, if we started the slow cooling from the liquid state till the room temperature as it becomes the solid, during that if we plotted, during that slow cooling process, if we plotted the curve temperature as a function of time, curve we will get a continuous type of curve. That curve will be termed as the cooling curve. In this curve we are going to plot temperature against time. Temperature against time. Then you will see now cooling curve of a pure iron. Now if you see carefully, plot here temperature above 1539 degrees Celsius, it will be in liquid state. It will be in liquid state. If temperature drops below 1539 degrees Celsius, then it will get transformed to delta iron, and this delta iron is having BCC crystal structure, and it will be a soft phase, that is this soft, malleable and ductile. Soft, malleable and ductile. Then this phase will last till temperature reaches 1400 degrees Celsius. Okay. Then when temperature falls below this 1400 degrees Celsius, it will get transformed to gamma iron. This is another allotropic form of the iron, and it will be having FCC crystal structure, that is face centered cubic crystal structure. Again this will be a soft phase, that is soft, malleable and ductile. Soft, malleable and ductile. Okay, this phase will last till your temperature reaches 910 degrees Celsius. It will last till the temperature reaches 910 degrees Celsius. Below that temperature, it will get transformed to beta iron. Beta iron, and this beta iron will be having body center cubic structure. Again, this will be a soft phase. It is soft, malleable and ductile in nature. Okay. This phase will last till the temperature which is 768 degrees Celsius. Now after this temperature, it will change to the alpha ion. This alpha ion will be having BCC crystal structure, and it will be soft, malleable and ductile in nature. It will be soft, malleable and ductile in nature. And now up to the room temperature, this phase will be continued. So this is the cooling curve for the pure iron. Now as I have explained from the liquid state to the solid state, again I will explain it from the solid to the liquid state, what exactly happens, so that you can carefully or you can clearly understand that what will be the changes during the there will be rapid change when you are using the rapid cooling or a rapid heating process. Now this is regarding the cooling process. Now I will explain regarding the rapid heating process or slow heating process, what will happen. From room temperature up to the 768 degrees Celsius temperature, it will remain, or iron will be in the form of alpha iron, that is it will be in body centered cubic structure, and its properties will be, it will be soft, malleable and ductile in nature. Then above 768 degrees Celsius, it becomes transformed to beta iron. It is having this crystal structure, it is soft, malleable and ductile in nature. And what is the difference between alpha iron and beta iron? As I have already told that the alpha iron will be magnetic in nature, and this above this all irons will be non-magnetic or paramagnetic in nature. Then this beta iron is last till temperature reaches 910 degrees Celsius. Then when temperature increases beyond 910 degrees Celsius, this beta ion get transformed to gamma ion. Then this lasts till in the range 910 to 1400 degrees Celsius. Above 1400 degrees Celsius, gamma ion get transformed to delta ion. It is having BCC crystal structure, and this phase lasts from 1400 degrees Celsius till it reaches its melting point, that is 1539 degrees Celsius. So this is the nature of the cooling curve for the pure iron. Okay. Now we have completed the 2 points, that is allotropy of the pure iron and cooling curve of the pure iron. Now this will be very helpful to understand the main point, that is the iron and carbide equilibrium diagram. So we will move towards that diagram. Now, first we will draw the iron carbide equilibrium diagram. Now, it is denoted by FEPC diagram. The iron carbide equilibrium diagram, or in some books they have mentioned that it is FEC diagram. That is iron carbide diagram also, we can say that. Now I will draw the exact equilibrium diagram. Okay, it will be like this. Okay, on y-axis we are taking temperature. Okay, it is in degree Celsius, and on x-axis, as you are aware of these things, that is equilibrium diagram. It is a diagram which will indicate the phases existing in a system at a particular temperature and a particular composition. And in this diagram, on y-axis, that is on the ordinate, we are plotting the temperature, and on x-axis, this is the y-axis, and this is the x-axis. On y-axis we have plotted the temperature in degree Celsius. On x-axis we have to plot weight percentage of element. Here carbon, we have taken carbon, that is in bracket you can write composition of carbon percentage, the weight percentage of the carbon.